All right. Okay, so steepest descent is really following. So if I'm minimizing j of x, and I have two pieces of subroutines available to me. One is to compute j of x given x, and two is compute the gradient of j at x given x. Then I can do steepest descent. I don't need to know any other aspect of j. I just need these two functions that computes j of x and gradient of j of x. So steepest descent is basically saying that I start from an arbitrary x0, my initial condition, my initial guess for my optimization. I think we use the s as our optimization parameter. So let me just trying to be consistent and use s. Okay, start from s0. And for if given sk, so k is 0 initially, my sk plus 1 is going to be sk minus a step size, let me say lk, times gradient of j at sk. Okay, so that's the procedure of steepest descent. It's called steepest descent because the direction I'm following. So first of all, lk is a scalar, right? It basically determines how far am I going when I step from sk to sk plus 1. And then this is the vector. This has the same dimension as the dimension of my design parameter s. This is a vector that determines which direction am I going when I'm stepping from sk to sk plus 1. And it's called the steepest descent because this gradient is the steepest direction in the sense that so this sk is the steepest in that if I take an infinitesimal step given a small enough epsilon, okay, sk minus epsilon times this, if I look at the objective function, is equal to the minimum of any j of sk times epsilon times a v for v being the same magnitude as the magnitude of the gradient. All right. So basically means that if I take the step size of the same magnitude, right? Epsilon times v. If magnitude of v is equal to this, then epsilon times v is the same magnitude as epsilon times the gradient. So if I follow the gradient direction, I'm really minimizing the immediate benefit I'm gonna get if I step for a small step, right? So can somebody tell me why that is the case? Why am I minimizing the benefit I get in a small step by taking the gradient direction? Well, the answer to that question maybe can be visualized in a contour plot. If I'm taking a very small step, I'm really zooming in locally near the starting point, sk. Any smooth objective function when I'm zoomed, so if you think of a contour map, if I zoom in and zoom in and zoom in and zoom in locally, what does the contour map look like? It looks like a linear slope, right? So So it's going to be looking like a linear slope where the contours are equally spaced and parallel to each other. And SK is going to sit right over here. Now imagine I want to take a fixed small step, which is basically I'm going into a point that lies on a fixed radius around this point. Which direction should I go? Where on that circle should I go to have the most decrease in the objective function?
Perpendicular.
Yeah, the direction that is perpendicular to the contour, right? And in the downhill direction, whichever that direction is. I didn't draw clearly, so maybe it's this way or that way, right? So that's why we actually follow the gradient direction. That's when I have a small step, that's the maximum gain I can obtain. So all of this makes sense, right? So why do we use anything other than the steepest descent? The only reason we don't always use steepest descent is that my step size, LK, is not always going to be infinitesimal. How big of a step I can take doesn't actually depend on the local contour, but depends on how that contour actually changes as I step further and further away. So what dictates how that contour changes as I follow that direction? The second order derivative, right? So if I follow that direction, let's look at a different plot. Let's look at J versus LK. Right, LK is here. So when LK equal to 0, my J is equal to JSK, right? As I take a finite, if I take an infinitesimal step, my drop is going to be exactly predicted by the gradient. But as I step further away, my objective function is going to flatten out and finally increase, right? So how far can I take to get to the minimum is determined not just by the gradient here. The gradient is going to predict you are going to decrease forever if you use the Taylor series. Yes?
Can you reiterate why it flattens out and then increases?
Oh, so why does it always flatten out and increases? Because if it never flattens out and okay. Well, it's actually not always the case. So it ultimately is going to flatten out, because if it doesn't flatten out, then the objective function does not have a minimum, right? So it's just going to keep going. Okay, and if it doesn't increase, then basically it means you want to take as large step as you can, right? So basically the assumption is that we are looking at a objective function that is actually has a minimum, and the minimum is actually somewhere in the inside of the domain, right? So that's actually the common assumption in doing analysis on the unconstrained optimization is actually that. First of all, you have a minimum, and the minimum actually lies in the interior, other than like so if your minimum lies in infinity, it actually means you don't have a minimum. Okay.